done, kinetic energy and the work energy theorem. In that work energy theorem, we discuss about, or we can state this work energy theorem, which is nothing but, easily we can state this work done, which is basically the force acting on that body is equal to change in its kinetic energy, or simply the difference between kinetic energy of final minus kinetic energy of initial. Now we are moving to another point, which is nothing but this work done with a constant force. Simply we define the work done. If you apply the force, this body will be moved or displaced from some distance. So here in this topic we discuss about the magnitude of that force. In that conditions, here we are applying the constant force. So basically here we again define this work done. So this work done basically we can define as, but if you apply the constant force, here we are applying constant force. So with the application of that constant force, which is nothing but the work done with the by applying the constant force is equal to the product of magnitude of that force. It is basically the product of magnitude of that force and the distance covered by that body. It is the product of magnitude of that force and the displacement, or this is simply distance which is covered by that body in the direction of your applied force. This body will be, the distance will be covered by that body, and which in the direction is that the applied force. The direction basically we can define in the application or at the applied force. So we can defining here this F, in that condition your applied force is constant. So your simply the work done is basically the product of magnitude of that applied force and the distance which is covered by that body. So here we are just consider the force which is acting on the body, which is nothing but this M, and if you apply this force, if you say this force which is acting on the body, then this body will be displaced with a small displacement or small distance. We can say that this is which is displaced with a small distance ds. So and this displacement will be happen in the direction of applied force. So we can write the work done, which is nothing but the product of magnitude of applied force and the small displacement. So F into ds. So this is your the magnitude of that applied force, and whatever body will be displaced with a small displacement, small distance ds. So this is the product of magnitude of that force and distance will be covered by that body, or we can simply say that F into ds. So we can write F into ds. So this is the work done of that body. So if you calculate, or we can say that the work done during the finite displacement. So if you consider here the finite displacement, which is nothing but s. So this s, again this displacement in the direction of that applied force. So here the direction is the applied force. So again we can defining the work done W for that finite displacement. For the finite displacement, this W is nothing but integration of F dot ds. So from this W is equal to F dot ds, we can determine simply this total work done. So our title, or initially I told about that this force. Here we are applying the constant force. We are applying the constant force. And if this force is constant, then if this force is constant, then your work done, we can say that W is equal to, we can take F is outside because our force, applying force is constant. So it becomes integration of your simply the displacement. So this integration is nothing but F into S. So the work done is equal to F into S. Here we are considering or taking some example or simply check with some example. Okay. So in your whole topic we are taking the constant force. So for that constant force we have to calculate this work done. So consider that if you apply the constant force along the direction which is making an angle theta. So here we consider one block. Okay. So consider this block on any surface, and in that conditions we are applying the force. So here we are applying the constant force. Here we are applying the constant force, and you know that if you apply the force to any body, this body will be able to move, this body will be displaced. So if this force is very slow, in that conditions there will be a small displacement, or this body will be displaced in the infinitesimally small. And if you say this force is acting here along, when this force is acting, this constant force, not only force, this constant force acting which is along the direction making an angle theta in the direction we will have in with the direction of that displacement. So this is your applied force, or here you can considering in that condition here this work done by that constant force which is obtained by resolving force. Here there is the resolving force into the two rectangular component system. Here there is a two rectangular component system. We can say that, or simply before that you can say if you apply the force, this block will be displaced or this will be moving. Again apply the force, again it will be moving, and this is considered at the initial position, this is at your final position. So if you apply the small force, this body will be displaced from point A to somewhere point x1, from x2. So in that condition, this is nothing but small displacement. So if you apply the force, the body will be able to move, or this body covers small distance, small infinitesimal distance ds, and by covering all these points, this body with applied that constant force reaches at the final position, from initial to that final position. So with that constant force, this body covered the total distance which is nothing but, you can say that from A to point B, which is nothing but whole distance s. So by considering this small displacement ds, which is reaches to the final condition, final points, which is nothing but the B, which is total distance s. So in that conditions, we are applying the constant force, and body which is able to move or displace to end point with a distance s. Okay. Now we are considering one more conditions are about the forces. So in that condition, this constant force is obtained by resolving force into two rectangular components. So here we can say f of x, this is nothing but f of y, and this is our force F. Okay. So your force, resolving force into your two rectangular coordinate system, which is along the x and along the y component. Now we are considering the magnitude of the two components. Magnitude of two components. So, first one, which is we are considering the f of x, which is along the x-axis. This f of x, which is along the x directions, the displacement is the ds. Again, this displacement, this body will be able or displaced with this distance ds. So in that condition, which is along the x directions, this f of x is nothing but f cos theta. In first condition or first component, which is along the x, this fx is equal to f cos theta. Now your second rectangular system, we are considering this f of y, which is along the y direction. So in that condition, your f of y, which is along the directions perpendicular to displacement. In that condition, this fy, which is along the directions which is perpendicular to your displacement ds. In that condition, this f of y, which is nothing but f sin theta. F sin theta. So these are two components, two rectangular system component, f of x, which is along the x direction, second one is along the y direction. In that condition, you get two components. Now, already we discussed about this condition. These two conditions are the force which is applied in the direction or in a perpendicular direction to that displacement. So in that component system, this f of y does not or does no work in the system. So this body does not move. So if this f of y or this force is perpendicular to the displacement, in that condition there is no work done. So this component is 0, and you can say that your dw is nothing but f of x into your displacement ds. Now here, but you know that this f of x is nothing but f cos theta. This f of x, which is nothing but f cos theta. So our dw is equal to f cos theta ds, or we can say f dot ds cos of theta. Here this is simply the dot product between force and displacement, and you can write here, we can write f ds cos theta is equal to the dot product of force and displacement. From this f ds cos theta, which is equal to the dot product of force and displacement. Also we can say that the work during a finite displacement. Here work during the finite displacement, we can write w is equal to integration of f dot ds. But you know that this force is constant. This force is constant. We can write f into ds. Again, this integration, this finite integration, we can say that which is nothing but f dot s. Here we can write f dot s, or which is nothing but f s cos theta. This dot product between the force and distance, which is nothing but distance which is covered by that body. This is the dot product of force and distance. We can write f s cos theta. So from these equations, from both these two equations, we can again define this one definition for that work done. Here we can again, because we are checking the work done with a constant force. There, in that all the conditions, the force which is applied to on that body will be constant. So here the work done by that constant force work done by that constant force may be defined as dot product of here, or here we can check that this work done by that constant force is a dot product of applied force with applied force and the displacement produced by them. This displacement produced by them. It is a very simple definition of the work done. Again I am repeating, this work done by that constant force. This work done by that constant force is the dot product of applied force and the displacement produced by that force. It is a very simple definition. Now, from this your equation, from all these equations, it is clear that the amount of that work done here, that amount of that work done is by that constant force. Here, that constant force which is depends on only the endpoints. From all these equations, you get by the dot products of work done. Here dw is equal to f dot ds, or w is equal to f into s, force into your distance covered by that body, which is nothing but s. So here we can see that the work done by that constant force which is depends only on the end points. Again here we can see that from A to B. So here the work done which is depends on the end points, not the intermediate path. Not the intermediate path. Again if you consider the round journey, here also if you consider the round journey, then the work done is equal to 0. Here if you consider the round journey, because in that condition if you considering this work done is only depends on the end point, not on the intermediate path. So again if you considering the round journey, then the total work done will be again become a 0. Okay, and if you want to take the examples, again you can consider the gravitational force between the two massive bodies. So in that example, the gravitational force between the two massive bodies, the round journey or this total work done on that body will be 0. Here we are just taking the work done for that constant force, and here we can get basically the dot product between the applied force and the displacement. It's simply the dot product. Okay, now we have to check some conditions for that dot product. If you considering here this work done in that all the conditions, the work done by that constant force, it may be a positive, it may be a negative, or it may be a 0. Here this work done may be positive, may be negative, or 0. We just check for the round journey. In that round journey, your work done which depends only on the end points, not on the intermediate part, and in that round journey or a closed loop, we can see this work done will be 0. If you consider, there may be a positive also, it may be a negative also. If you consider the force, the applied force and this displacement in the same direction, you are considering if this force and displacement both are in the same direction. In that condition, this theta is equal to 0. If you considering this applied force and the displacement in the same direction, in that condition our theta which is equal to 0. If you considering your function, this equation the work done which is equal to f s cos theta, in that condition our theta is equal to 0, then cos theta is equal to 1, and this w is nothing but, which is nothing but this cos theta is equal to 1, so f into s, basically it gives positive value, or here there will be a positive work done. In that, for example, if you consider free falling body by the gravitational force, there is, if you consider the body fall freely in the gravitational force, there will be this work done will be positive. In that example, we can see the work done will be positive. Now, we check second condition. Any other more condition? If you applying force and displacement, if you considering this applying force and this displacement is perpendicular to each other, it will be perpendicular to each other. So in that condition, this theta is equal to 90 degree. If you considering this applying force and the direction, this displacement or distance in that here, both are perpendicular to each other. Here we can see that. Consider this block which is having mass m. This is displacement and we are applying the force. This force in which is both are perpendicular to each other. In that condition, this theta is equal to 90 degree and cos 90 is equal to 0. Here, this cos 90 equal to 0. If this cos 90 is equal to 0, again our function, this w is equal to, which is basically f s cos theta. But this cos theta now, for the angle 90 theta is equal to 90, cos theta, cos 90 is equal to 0. This work will become 0. So, if this body will move to the perpendicular direction, to the direction of that force, so if you considering, if you applying the force which is perpendicular to that directions, in that conditions there will be no work done. There will be no work done, or we can say that work done is 0. We can say this work done is 0. Okay, this is in first condition, you are applying force and displacement or this distance covered by that body in the same direction. In that condition, you get the positive work done. And in your second case, we can see that this force and displacement which is perpendicular to each other, in that condition, the work done is 0. Now, in our last lecture, we can take one small example which is nothing but the pulley, okay, on the railway track. In that condition, when this pulley move on the railway track or platform with their load, or we can say simply luggage, in that condition also we check this work done by that pulley is 0. Again in that condition, this work done by that pulley is again 0. Okay, and now there is one more conditions. There is third condition. This applied force and this displacement. This applied force and displacement are in the opposite direction. In first case, both are in the same direction. There we get the positive work done. In the second case, this force and this displacement is perpendicular to each other. In that condition, you get the total work done is 0. Now, the third case, this force and displacement in the opposite direction. And if you consider in the opposite direction, this theta is nothing but the pi or 180. And in that condition, this cos pi is nothing but the minus 1. This cos pi is nothing but the minus 1. Again, we can say this w. So, this work done is nothing but the dot product of force displacement. So, here we can put this cos theta. Theta is pi, cos pi is minus 1. So, you get minus f into s. You get minus f into s. It means that you get this negative sign, and this negative sign indicates the negative work done. Here, negative work done. So, if this force and displacement both are opposite to each other, in that condition you get negative work done. Where we can observe this, there is a, if you want to check the example, for that we can consider the positive and negative charges. So, if you consider Just consider the two charges plus Q, small and capital Q. Okay, in the two charges we can say these move toward each other. Here you can see that both are okay. If you considering the two positive charges, when these positive charges which is moving towards the positive charge, this small q charges positive toward to capital or positive Q. In that condition, their direction will be opposite to each other. In the here in that example, their force and displacement both are opposite in the opposite direction, and in that condition you get the total work done is negative. Here we can observe the total work done by the two charges. Here this force or this total work done is negative. It is must be noted that this work done by the applied force, work done by applied force is positive. Here this applied force is